Not for a while. I came here on the 15th of September.
Ah.
And I'm here for another couple of weeks.
Oh.
And then I'm off to Barcelona again.
So is where there is the Basque Center by any chance?
No, this is I'm actually well, I'm not in a subterranean lab, but these are the offices of a subterranean lab that it's here in the middle of the Pyrenees.
Ah, similar to the one in Abruzzo where they have a
yes, exactly. It's so this is the subterranean laboratory of Canfranc, and actually the former director came from Gran Sasso.
Ah, what kind of research they do there?
Well, this is actually a sort of particle physics lab, but because they have this tunnel with 800 meters of mountain on top of them, they can do research on living systems at very low radiations, and we are sort of interested in that. So I came here. So they're interested in modeling what happens, and
yeah, it's like in Gran Sasso, you are shielded from radiation because of the mountains. So yeah,
it's very nice, very nice.
Yeah, oh, great. Okay, so we're almost. So I put the YouTube before I forgot, and then I have to start recording. There are all these, sometimes I forget some of the stuff, so I cannot forget. So I think we 1 second, someone, okay, Philippe. Right, I think we could, we are on YouTube, and let me put you, and here the YouTube, and we can start, and then eventually people can join us later. So let's start recording. Okay, so great pleasure to have Thomas with us. I still remember the first seminar of Thomas in 2004 in École Normale of Paris, where he introduced his this very nice model about cancer modeling. That it's always it's beautiful. So I always include in all my lectures. So I'm sure it will be inspiring mini course also once more for everyone. So he's currently at the Centro de Ricerca Matematica, Bellaterra. Well, in principle, his permanent position now he's in the Basque Country, where he served as a deputy director. Here, 1 second, Carolina. And he's leading research in many topics of dynamical system applied to biology. Always very interesting application. So please, Thomas, floor is yours.
Well, thanks, Stefanella, for the invitation to give a course in this lecture series. So as you can see here at the bottom of my slides, I'm recycling because this is a topic in which I have been asked to lecture several times over the years. So well, I've heard that you come from very different backgrounds, so I will try to keep it simple for everyone, but interesting for everyone as well. And let's see what we achieve. If someone has a question, please interrupt or put the question in the chat, and Stefanella will pass it on to me. Okay. So the first lecture today, it's well, we will see, because this is elastic. We will see if there are not so many questions. Perhaps we will start with the second lecture today. But I'm going to give you first sort of an introductory lecture on basically on motivation. why it is important to study stochastic effects. So one could think, well, just using deterministic modeling like dynamical system theory and things like that, perhaps we should have enough. Sometimes it's enough, but sometimes it's not. So what I'm going to start with is I'm going to give you some motivation examples of what we called noise-induced phenomena. So this is phenomena that occur in stochastic systems, but cannot be observed in deterministic systems. Okay, so that will be the first part of the lecture. And then I'm going to start by giving an idea of how we model this noise-induced phenomena. So I'm going to start by introducing what the master equation is. We will see a derivation from sort of first principles in lecture 2. I don't know if that's going to be on Thursday or it's going to be later today, depends. I'm going to tell you what the law of mass action is, which is the sort of basic model that we use when we do stochastic modeling. And then a couple of sort of topics in which we will sort of fiddle around with this concept of steady versus absorbing states. So we will see that the concept of what a steady state is in a stochastic system is not so straightforward as, for example, in a dynamical system. Okay, so we will see that this distinction is based on that. And then I will show you something that unfortunately we cannot do very often, which is analytical methods to solve this. So what we will see is that these systems are usually quite complex, and even relatively simple systems cannot be tackled analytically. But with some very simple models, some linear models, we can do some analytics, and I will tell you at the end of this first lecture about these analytical methods. Okay. So well, these are general references on stochastic processes. By general references, I don't mean that they are good books. I mean they are general references that are the ones that everybody recommends. But well, since I'm being recorded, I'm not going to be politically incorrect. But yeah, there they are. Okay, so these are two general references, mostly dealing with physics and chemistry. And then there is a specific book. This is a rather nice book. The book by Linda Allen, I do recommend. It's mostly for mathematicians, but there are also some nice applications to biology. So for the most mathematically inclined, particularly the ones that like biology, I definitely recommend Linda's book. Okay, so I will give you, for specific issues, I will give you literature as we go. Okay, and with this, I'm going to start with a motivation. So there exists the idea, particularly among mathematicians, that randomness and noise are simply sort of unsystematic additions or perturbations to a well-defined average behavior. Okay, this sometimes is true, but sometimes is not. Okay, so what I will present now is several examples of systems in which noise affects the behavior of the system in a non-trivial manner. Okay, and it's actually fundamental to understand the sort of how the system actually works. Okay, and from these examples, I will try to extract some rules of thumb for see when randomness plays a role. Okay. So the first example is basically it's bistable systems. Okay, so I'm giving here an example from biology. I'm not going to explain what this G1S transition is. If someone is curious about the biological motivation of this model. That you can go to the reference here and look at it. So this G1S transition has to do with cell cycle, that is with cell proliferation, okay, with the things that happen inside the cell when a cell is trying to divide, okay. And one of the modules of this model has this form, okay. So these Y and X would be the concentration of certain proteins that interact in a particular way. We are not going to go into the details of that, okay. And this particular system has the property that for certain values of the parameters is bistable, okay. So you can see this. By the way, can you see my pointer when I move it?
Yes.
Okay. So you can see this here. So here I have plotted in red the null line for the Y variable. So this would be this red curve here. Okay, and the blue one is the null line for the variable X. Okay, and we can see here very easily that these two curves have 3 crossings. Okay, and well, by inspection, or you can actually do the linear stability analysis and all these things. You can see that this point here and this point here are stable fixed points, and this one here, this intersection here, corresponds to a saddle. Okay. And because this is a saddle, there is a line that goes through the saddle and goes somewhere through here that it's a separatrix. Okay, so this is a line that separates this or splits this phase space into regions that correspond to the basin of attraction, to the basins of attraction of each one of these fixed points. Okay, so and in the deterministic system, so we can see here 2 examples. Okay, once you fix the initial condition, the long time behavior of the system is fixed by the uniqueness of the solution. Okay, so in this case, this initial condition belongs to the basin of attraction of this fixed point, and this is the evolution. And this initial condition, that it's very close, but on the other side of the separatrix, sort of evolves towards this fixed point. Okay, and in the deterministic system, this is it. So if you have if the initial condition is on either side of the separatrix, the final fate of the system is decided. Okay. Well, the picture the picture that emerges when you consider that this system of equations here is the deterministic limit or the mean field limit of a system the dynamics of which is driven by intrinsic noise, is completely different. Okay, it's completely different in the following sense. So what I'm showing here, so for example, you can see this green trajectory would correspond to something like to this one here. Okay, so this is the one whose initial condition is such that you are going to evolve to this fixed point here. Okay, so but what happens when I generate with methods that I'm going to tell you later on in this course? I can generate stochastic realizations of the system, starting from the very same initial condition as that we use for the deterministic simulations. Okay, and in the deterministic simulations, once you fix the initial condition, the evolution is fixed, and you end up in this fixed point here. Okay, so the first thing that you can see when you do this stochastic simulations is that you lose the notion of uniqueness that you have in deterministic dynamical systems, because now from this same initial condition you can sort of get something that reproduces quite well the deterministic dynamics. Okay, you can see this green dashed line that sort of follows not exactly, but quite closely the deterministic trajectory, and it goes to this. It's ends up sort of fluctuating around the deterministic fixed point. But you can have other realizations of the system that, starting from the very same initial condition, they take you to the other one, to the other fixed point. Okay, and the other way around. Okay, so if you start from an initial condition like this, that in the deterministic system would take you to this fixed point here, what you get is that, well, sometimes you do when you have noise, but sometimes you cross the separatrix and go to the other fixed point. Okay, so this means that as we say here, in a system affected by noise, the separatrix is no longer a separatrix. It turns into a barrier. Okay, and in fact, this is telling you that you can have, in a stochastic system, you can have transitions, you can have random transitions or noise-induced transitions between these two fixed points. Okay, and this gives actually rise to a rather nice part of probability theory that it's called large fluctuations, in which you study exactly these transitions. Okay, so these transitions are forbidden in deterministic systems, but they actually control the long-term behavior of an stochastic system, because what you are going to have is that you're going to have transitions between this point and this point. So most of the time, the system is going to stay fluctuating around here, but from time to time, you're going to have a large fluctuation that is going to take you the system to the other side of the separatrix and the other way around. Okay, so this is a first example of a system in which if you consider that you can have noise, so bistable systems or multi-stable systems in general are candidates for behavior that it's not sort of recapitulated by the deterministic limit, in the sense that you have these noise-induced transitions. Okay, so any questions? No? Okay. So another example of this of systems that have this noise-induced phenomenon is this Moran process. Okay, so the Moran process, which is named after this Australian statistician guy, is a variant of the Wright-Fisher model. Okay, and in fact, it's a particular case of what probability theorists call Orn models. Okay, so basically, I'm going to describe the dynamics of this system. It's very simple. So we consider n individuals of two types. Okay, so in this case, we have green balls and green individuals and red individuals. Okay, so but the green and the red are it doesn't matter. Okay, so we will normally refer to normal and mutant individuals because this model is used in population genetics, but it's just a name. You don't have to bother about this. Okay, so we start with a total of n individuals of the two types, right? And the total number of individuals is kept fixed. Okay, so this is a rule of the dynamics. Okay, so we will consider that at time t, we will have n normal individuals and m mutant individuals. So that at every time for all t, n plus m is equal to capital N. Okay. So the dynamics of the system or the time evolution is given by this kind of recipe here. So at each time step, one of two things can happen. Okay, so we can have that either the number of normal individuals is increased by 1, and therefore the number of mutant individuals must be decreased by 1 because capital N must be constant all the time. Okay, or we can have the other way around. So n goes to n minus 1 and m goes to n plus 1. Okay, and the probability or the rate, the probability rate at which these two events happen, basically are determined as follows. So basically, for this event here, which I will refer as birth, okay? So for the birth event, I will choose one green individual, one normal individual at random, which happens with probability n, small n divided by capital N, okay? Because I'm considering that all the normal individuals are identical and all the mutant individuals are identical. So the probability of choosing one at random is just one normal individual at random is just n over capital N. Okay. So I'm going to choose one at random, for example, this one. And what I'm going to do is to duplicate that individual. Okay. So that will produce a birth in the normal population. Okay, and then because I need to keep n constant, because that's the requirement of the model, I need to get rid of one of the mutant individuals. Okay, and for that, what I'm going to do is to choose a red ball at random, which happens with this probability here. Okay, and I'm just going to remove that individual from the pool. Okay. And for the death event, I'm going to do exactly. So the probability of the death event is done exactly in the same way. So I'm going to choose a normal individual at random, and I'm going to remove that individual, and then I'm going to choose a mutant individual at random, and I'm going to let that individual to duplicate. Okay. And that happens with this probability. Okay, is that clear? So it's very simple. I'm not sure I have explained it very clearly, but basically it's you just pick up one of the individuals, duplicate, pick up one of the other individuals, and remove. And you do that in these two possible ways. Okay. So the first
question. There is a question. What is the difference between W plus and W minus? There is a question.
Well, in this particular case of this particular model, there is no difference. Okay, so this is okay. So you know, I'm choosing this particular formulation because it gives me a nice example for illustrate what I want to illustrate. Okay, but for example, in this usually what you would have is, for example, here the rates, the W plus rate would be multiplied by a K plus constant, which would give sort of an idea of what's the time scale for the birth. And the same here, there would be some K minus constant that would give us the time scale for the death. Okay, but in this particular case, just because I want to illustrate what I want to illustrate, which will be clear in the next slide, I have chosen it like this. Okay, so and as the person in the audience has sort of spotted very well, the point here is that W plus and W minus are equal in this particular case. Okay, and therefore the average of the increase in the number of n is equal to 0. Okay, and if you do the maths, what this thing here implies is that the number of normal individuals, the average of the number of normal individuals is constant in time. Okay, so this is because you have the same probability of increasing by 1 than decreasing by 1. So on average, right, things are going to stay the same. Okay, so this would be kind of the mean field dynamics. The equation 1 here would be the mean field dynamics for this particular system. Okay, so n, the average of n is equal to a constant. However, again, when we run simulations of this model starting from the same initial condition, what we see is that the dynamics is very different from this. Okay, In fact, this never happens. And what happens is that, for example, like in this green trajectory here, can you see this screen properly, or?
Yes, yes.
Yeah,
yes.
you can distinguish the colors. Okay, great. So as you can see in this green trajectory here, what happens is that the number of n is fluctuating in some sort of random manner, and eventually all the individuals in the box, right, would become green individuals. Okay, whereas in this red trajectory here, we see that we start with the same initial condition. This fluctuates, it goes up and down, blah, blah, blah. And eventually it will hit n equal to 0. So which means that all the population has turned red. Okay. And this happens every time you run your system. Okay. In fact, because these two states are absorbing states. Okay, absorbing states means this. Okay, that the probability an absorbing state is a state which you have positive probability of reaching, but the probability of going out of that state once you have reached it is equal to 0. Okay, so this is basically what you have here. Okay, so the fact that these systems are the fact that n equal to 0 and n equal to n are absorbing states means that the limit or when time goes to infinity of this probability, so the probability that n becomes 0 or n becomes n is equal to 1. Okay, which is completely different from this. Okay, so in fact you are never going to observe this. So the closest thing that you are going to observe to this is a trajectory like this darker one, okay, in which you start with some initial condition, and this goes down, it goes up, it goes up, it goes down, it goes down, and but eventually you are going to reach one of the absorbing states.
Can we predict? Can I ask a question? So
Yes.
Can we predict the average time we'll need as a function of the size of the system to reach this absorbing state?
Yes, you can predict that. Well, in this case, you can predict it, okay? Because this is a sort of very simple and stylized system. But in this case, I'm not going to go into the details of how you calculate these things. But if you are interested, I can send you bibliography on how to do this.
Okay, thank you.
But you can in this case, well, in general, in one-dimensional birth and death processes, you can do some at least some asymptotics of how these heating times are distributed. When I say asymptotics, I mean with system size or inverse of noise. But you can predict that. Yes.
Thank you.
Okay. Okay. So is that clear, more or less? Yes. Okay.
Yes.
Good.
Yes.
So, and the last example is so I mean this is a very well-known equation for someone interested in mathematical biology. So probably this is the first thing that you learn when you are learning mathematical biology, and is the logistic equation. Okay, and the logistic equation has I mean it's perfectly well studied. So it has two steady states, n equal to 0, which is unstable, and n equal to k, the carrying capacity, that it's stable. Okay, and if you have a positive initial condition, the solution of this thing will approach asymptotically the value of k. Okay, but we can consider a continuous time Markov process which has this deterministic limit. Okay, so kind of a random version of this model. okay? And this system, okay, so this whatever stochastic version of this system that you want to study is going to have the feature or the characteristic that n equal to 0 is an absorbing state. And this is completely different from what happens here, okay? Because in the deterministic system, m equal to 0 is unstable. So all the trajectories are going to go away from m equal to 0. But this thing here means that once you reach n equal to 0, you are going to stay here, just like we saw in the Moran process. Okay, so what happens is that there's people still coming in. Okay, so what happens here, and this is yeah, this is well, this is just to illustrate what happens with the behavior of the system when you change the characteristic size of the system. Okay, so the logistic equation or the logistic system has a parameter here, this k, that is telling you how big your system is going to get, or asymptotically how big your system is going to be. Okay, so here in the case of the deterministic system, m is going to tend asymptotically to k. So k is somehow gives you an idea of the size of the system. Okay, so now this parameter is going to be very important in everything that the system size is going to be very important for everything that we do later, particularly everything that has to do with taking deterministic limits and things like that. Okay, and what happens is that as you can see in this example very nicely, I think, is that as k goes bigger, okay, so in the deterministic system, so here I have plotted n over k. Okay, so in the deterministic system, which I forgot to include in this graphic, but in the deterministic system, what we should see is something very similar to what we observe in the black line. Okay, so we start with an initial condition that is here, I think, n over k equal to 0.5, and then the population starts growing, and when it reaches 1, so when the population reaches the carrying capacity, it stays there. Okay, and this is what happens, for example, when you consider k equal to 1,000. Okay, so k equal to 1,000 corresponds to this black realization over here, which behaves very much as the deterministic prediction, kind of. Okay, so you start with an initial condition, this thing starts growing, and when you reach the carrying capacity, you sort of stay fluctuating around there. Okay, but what happens, so in this case, this means that the noise is suppressed here when you consider system size, bigger system size. Okay, because, for example, if you see at what happens with the system with k equal to 10, which corresponds to this red line here, so what you see here is that the fluctuations are much bigger, and eventually you will hit the absorbing state and being there. Okay, so this means that for a small k, that is big noise, okay, fluctuations dominate the behavior of the system, and extinctions are very common. Okay, so this is just to contrast the behavior of the sort of more deterministic like system with the behavior that you get when the system is smaller and it's dominated by noise. Okay, so is this more or less clear? So this idea that system size suppresses noise is going to be clearer when we look at how we do the simulations. Okay, when we look at the Gillespie algorithm, so what we will see is that when we have big system size, the system undergoes a lot of transitions. Okay, so if you look at the behavior of the system in a fixed window of time, when you have k equal to 1,000, what you will see is that there are a lot of stochastic events, and because you have a lot of stochastic events, there is kind of a central limit theorem kind of result taking over the dynamics of the system. Whereas when you have k equal to 10, so system size very, very small, what you see is that in that same window of time, you are going to see much less stochastic events. So that's why basically then the system is dominated by noise. And you can actually see this thing here in the simulations. Okay, if you see the black line here, so I have plotted all these steps in the simulations in here. Okay, so if you look at the black line, you can see that the black line, I mean, it's not smooth, obviously, but it's much smoother than the red one, obviously. Okay, and that the system sort of becomes smoother and smoother as you increase the system size. But it has to do with this sort of statistical self-averaging of the system when you have very big sizes. Okay. So this would be sort of to recapitulate the motivation. Well, we have seen actually 3 examples of 3 different mathematical descriptions of the same physical biological systems. And we see that when we, in these 3 specific examples, when we see, when we look at the deterministic limit, we don't obtain the same kind of behavior as when we look at the system with noise. Okay, so this will happen. So this is not an exhaustive list, and so these are rule of thumbs that I'm going to give you now. But basically, when you know, in the most common situations, particularly when you are looking at applications in biology, noise is going to be important when you have multi-stability, as we saw in the first example, because then you can have those switches between the 2 basin of attractions. Okay, and another big clue of that noise is going to be important if your system, if the stochastic system has absorbing states, because what happens when you have absorbing states in the stochastic system is, as we saw, that basically when you hit those systems, the system is going to stop there. Okay, and that is and that sits sort of in contradiction to what happens with the deterministic limit. Okay, so these two clues that noise may be important, maybe it's not always important, but it may be important, is when you have multi-stability or when you have absorbing states in your stochastic dynamics. Then you have to be careful when you go. If you try to use the deterministic limit of the system as some sort of proxy of what happens when in the stochastic system, you may get crooked answers, because as we have seen, when there are absorbing states, then the stochastic dynamic can be quite different from the deterministic limit or the mean limit. Okay, so now what we are going to do in the rest of these lectures is look at well, how can we describe, I mean, how this is possible, and how then above all, how we are going to describe these stochastic systems. Okay, so I'm going to now give you, as I said at the beginning, an overview. Stefanella, do you usually
Yes.
do a bit of a break, or?
We can do a break if you want.
Well, yes, I mean, this would be unnatural because it's I've been talking for, yeah, almost 40 minutes now. So
yeah, we can
yeah.
do 5 minutes.
Yeah, that'd be good. Yes, that's.
Yeah.
I mean, I can go on, but well, I can go on for hours and hours and hours talking about it.
No, we can do 5 minutes break.
Yeah,
And
that'd be good. Okay, so
okay, so 5 minutes, and in the meantime, people have a question. They can prepare the questions. So when we come back in 5 minutes, you can
okay.
ask. No,
Yes,
in the first
absolutely,
part.
absolutely. Yeah,
Yes.
yeah. Thank you.
And yes, so great lecture. So if there is some reference about this specific part, then you can example or article or something.
Mm-hmm. I will, yeah, and yeah, I thought I had some. I thought I actually had some references, but yeah, the next lecture I will give you.
Okay.
I will give a list of papers.
Okay, so we make a pause here. Then we have to remember to start again the recording, and we come back in 5 minutes. And if people want to ask questions, they can in 5 minutes. So everyone have a 5 minutes break. Okay.
Okay. Thank you.
Thank you too.
So let me see.
So we can go
start.
back. So I can let me start again, resume.
Okay.
Okay. So resume recording. So please, Thomas, there is a comment here from Armando. Armando, would you like to make it, or should I read it? Armando?
Yes, well, I can.
Yes.
Regarding the logistic growth case, I think that the system will always evolve to the absorbing state n equal to 0. The fact is that if k is large, that will take on average an extremely large time to happen. Probably that will be invisible to simulation. But anyway,
that's absolutely correct. If you look at the logistic system, eventually all of these lines, regardless of system size, will hit the absorbing point. And you are correct. I mean, the time that this takes is actually grows like exponential of the system size. Okay, so if you have a system size, if you have a very big system size, you have to wait an exponentially long time in order to observe this extinction. Okay, and this is why the mean field limit works when you have when your system is big enough, because all these stochastic transitions or all this noise-induced phenomenon that we were talking here, including these ones, the ones associated with this bistability, the waiting time for the system to pass from one basin of attraction to the other is exponentially long with the system size. So this is the reason why mean field limits tend to work if you have a system that is big enough. But you are absolutely correct. Yeah.
Thank you.
Okay. So if there are no more questions or comments, I will move on to the master equation. Okay, so again, I will give a sort of an overview today, and yeah, tomorrow I will give a more sort of first principles derivation of what the master equation is. Okay, so the master equation is going to be our fundamental mathematical description of I should say, a Markov stochastic process. So what this word Markovian means, we will see more in detail the sort of precise definition tomorrow. Okay, so this is going to be the sort of fundamental mathematical object that we are going to deal with. Okay, and in fact, as we will see, is a set of ordinary differential equations. But the thing with this set of ordinary differential equations is that it can be an infinite. So it can have an infinite number of equations. Okay, so for example, if you try to describe the sort of the stochastic logistic model, because in principle you don't have an upper bound to the population that you can have, so there is no theoretical or practical bound to that. You will have an infinite dimensional system of ODEs. Okay, but yeah, so basically this master equation is obtained as a probability balance for all the events that can occur during a particular time interval. Okay, and as I was saying, mathematically, it is a set of ordinary differential equations for the probability P of x of t, which is the probability that the number of individuals in the population at time t is x. Okay, so x here is in all the examples that we are going to see, the random variable is going to be discrete. Okay, it's going to be a positive, an integer variable. Okay, and well, the master equation has this form. Okay, So here, X is the Markov process. It's a random variable. In general, can be vector valued. In many of the examples that we are going to see, this is going to be a one-dimensional variable, but it doesn't need to. Okay. R is the number of possible processes that can happen in the system. So, for example, in the Moran process or in the logistic process that we saw earlier, we could only have two: birth and death. In general, you can have all sorts of things. You can have mutation, you can have binary annihilation, you can have everything that you can basically imagine. Okay, but R is the number of these processes. Okay, now these W's here are the probability rate. So that's the probability per unit time of one particular event to occur. Okay, so for example, in the case of the logistic process, we had two. Okay, so we had birth and death. Okay, and these were the rates. Okay, and R, this quantity here is the change in the value of X when event I occurs. Okay, so for example, in the case of the processes that we saw before, Ri could be +1 for a birth event or -1 for a death event. Okay, but again, in general, can be any integer. Okay, and this quantity, so this is kind of the mathematical definition. So what all this means is that the probability that your process at time t plus dt is equal to x of t plus ri, given that at time t was x, is equal to the rate multiplied by the time interval that we are looking. Okay, so these are plus order the dt squared corrections. So is that clear? These definitions?
Yes.
No questions? Okay, good. Okay, and the master equation can be interpreted as a balance equation where this term here. So if we are looking at state X, okay, so this is the rate at which probability is going to enter in. So if you look at this as a sort of balance equation, so this is like a sort of concentration coming into, or probability density coming into state X from all the possible states that are communicated with state X. Okay, and this is sort of probability. The second term is the probability of going out of state X. Okay, so this is how in fact normally I will now run you through a very simple example of how this is derived by you, but when you are doing some sort of modeling exercise, you don't go through the process that I will show you later. You just write this equation in this way, just thinking about the probability in and the probability out of a given state X. Okay. Now, in order to write a model, we need to provide two things. So we need to give some sort of expression to this rate Wi, okay, and we also need to give values to these quantities here, to the R quantities. Okay, and to do that, we usually, not always, but usually one of the sort of most popular models is the law of mass action model. Okay, so unless I'm told otherwise, I'm going to assume that you don't know what the law of mass action is. Okay, if I'm told differently, I will skip that. But if there is someone that doesn't know, I will go on with it. Okay. Well, as I was saying, to specify the model, we need to give an expression for the probability rates. Okay. So this assumption originates in chemical kinetics and consists of assuming that these W quantities basically have two properties. So basically, so the basic assumption here is that the system is well mixed. Okay, so this means that two molecules or two cells or two individuals of the same time are indistinguishable. Okay, so the probability of something affecting one individual, it's exactly the same as the probability of affecting the other individual. Okay, so this is this well mixed assumption. Okay, and with this well mixed assumption, we can assume that the rate of something occurring. So, for example, imagine we are thinking about a chemical reaction that involves interactions between one chemical and another chemical. Okay, so the rate at which these reactions are going to happen is going to be proportional to the number of combinations that we can form with these two elements. Okay, so that's the first part, and the second part is going to be that then this number of combinations that we can do with these two elements multiplied by a constant that it's going to tell us or it's going to inform us about the time scale for this reaction to happen. Okay, so for example, imagine that we have this very simple reaction. Okay, so we have X is now the number of some molecule, for example, or the number of cells or whatever, and this sort of decays into some product. Okay, now this can happen to any of the molecules or of the individuals X, right, at a rate K1. Okay, so the probability or the probability rate of this transition happening is K1 multiplied by X. Okay, now suppose that instead of this reaction we have this one. So we have that we have two types of individuals or two types of molecules, whatever it is, and these two combine together to give a product. Okay, so now what the law of mass action prescribes is that now the combinatorial factor, so how many couples of X and Y can we form? So we can form, if the number of X, so we can form X times Y divided by 2, because Y and X and Y is the same pair. Okay, so this would be this combinatorial factor that I was talking about before, and this is the time scale. Okay, and for example, another example, if we have that two individuals or molecules or whatever combine together to form a product, okay, then the rate is some sort of a time scale, in this case K2, multiplied by the number of pairs that we can form with two identical particles. Okay, so that then in that case the combinatorial factor is we can choose for the first one, we can choose among X. For the second one, we can choose among X minus 1, because we have already chosen one for the first one, and this is the combinatorial factor. And again, we divide by 2 because these are identical molecules. Okay, and we can play this game until we are tired of it. Okay, is this clear how this works? So basically, it's very simple. We assume that everything is well mixed. So then the rate is basically proportional to the number of combinations that we can form with the individuals involved in one particular reaction or event, and that this one part, and the other part is the rate. We multiply both together, and that's how we prescribe this rate. This clear to everyone? It's usually not.
Yes.
This may be a very clever audience, but I don't deny that. But okay, I will go on. If someone has questions, please interrupt. Okay, so now we are going to see sort of an example from deriving the rates to deriving the master equation in some detail. Okay, for a very simple system. Okay, and we are going to look at a linear birth and death process. Okay, so in this process, as the name suggests, there are two events. Okay, one that it's the birth, in which the population increases by 1. So I'm going to consider here that the x that we were talking before is now n, and it's a one-dimensional stochastic process. Okay, so n is the stochastic process, the number of individuals in the population. Okay, and we can have that by birth, the number of individuals is increased by 1. Okay, and according to what we just saw, this is an event of this type. Okay, so it's n without help from anyone else going into a product. Okay, so the corresponding rate would be n multiplied by lambda, which is the birth rate. Okay, and the second event that we can have is death. Okay, and this means that n is decreased by 1 in this case. And again, this process is of this type here. Okay, so the rate is going to be again n multiplied by some constant that's going to be the death rate. Okay, so now to derive the master equation. To derive the master equation, we have to write the probability balance for the probability of having n individuals at t plus some delta t. Okay, and so how can we have n individuals at time t plus delta t? Okay, so one way is that we had at time t, okay, we had n minus 1 individuals. Okay, and between t and t plus delta t, there has been a birth event. Okay, so what's the probability of a birth event? The probability of a birth event is W plus multiplied by the delta t. Okay, remember that the W quantities are rates. Okay, so the probability is that multiplied by delta t, if delta t is small. Okay, so now because at time t we are conditioning the system so that at time t the population was n minus 1. Okay, so with a population of n minus 1, the probability of a birth is lambda multiplied by n minus 1 multiplied by delta t. Okay, so this would be the probability of going into n by a birth. Okay, then there is the probability of going into n by a death event. Okay, and for that we have to condition the system so that at time t the population was n plus 1. Okay, and then the rate of a death with a population of n plus 1 is sigma, this constant here, multiplied by the population, which now is n plus 1. Okay, and this delta t is to give us the probability. Okay, and so this is the probability of going into n by a death event. Okay, and the third possibility to have n individuals at time t plus delta t is that at time t we already had n individuals and nothing has happened. Okay, so this is the probability of something happening, and 1 minus the probability of this is the probability of nothing happening. Okay, and the system stays with population n. Is this clear? Yeah.
Yes.
Okay, good. So now, sorry, I find this dynamics of the Zoom lecture, I find it very difficult. I'm sorry. I know I'm yeah, it's annoying, but okay. So now, so this is the full balance of probability. Okay. So now, by rearranging this, so we have this 1 multiplied by this p of nt, we move this to the other side, and so we will have here pn of p of n of t plus delta t minus p of n at t. We divide the whole equation by delta t, and we take delta t equal to going to 0, and what we get is this equation here. And this is the master equation for the birth and death process. Okay, and if you look at this equation, okay, so this is exactly the same as this one here. Okay, because in the case of the birth and death process, capital R is equal to 2. Okay, and what we have here is in the negative term, we have the sum of all the rates multiplied by the probability of in this case x or n, which is exactly what we had here. Okay, so this last term here is exactly the same as we had there. And the first one, sorry, this is exactly the sum over all the possible events of the rate multiplied by the corresponding minus the corresponding R, which is this one here. Okay, so we had, remember that in the master equation, in the general formulation, we had here minus Ri. Okay, so for the birth event, minus Ri is -1, and for the death event, minus Ri is +1. Okay, so this has exactly the same form as the general form that we looked at earlier. Okay, and the way in which you would normally write this is just by looking at well, this sort of balance structure. Okay, so you can have this is the rate of going out by either birth or death. Okay, and this is the probability of going into state n, or the probability rate of going into state n by birth or by death. Okay, so that's how you would write it.
Sorry, I have a question. So after
Yes.
each delta t, you can have a birth, have a death, or have nothing, but can you not have both a birth and a death?
No. No, not well. You can, I mean, in this with this model, sorry, with this model that I'm using here, you can't. You can have more complicated models. Okay, so for example, you could have, but also think that yeah, I mean, the problem is that look at the problem is here. Okay, so we are assuming that delta t goes to 0. Okay, so what you're saying, the probability of having a birth and a death would be something of order delta t squared. Okay, so when you do this limit, this would just be washed off.
But I'm just curious because the third term you have in the equation 5 is
Yes.
represents the case where neither birth nor death happens.
Yes.
Then if that can happen, then I just thought you would also have a term for both.
But again, I mean, yeah, I mean, perhaps we can discuss this offline. But if you think about it, if you want to have two events happening at the same time, you would have the probability of that would be W plus multiplied by times W minus times delta T squared. Okay, and because you are taking here this limit, if you do the maths, you will see it immediately that when you take delta T going to 0, those events sort of get washed off because they will be order delta T in this. Oops, sorry. Sorry, I didn't disconnect my telephone. So yeah, is that clear?
Yeah, you're saying that both happens as a delta T squared kind of, and that
Exactly.
drops out when you send it to 0. Yeah, thanks.
Yeah. Well, it's a bit of a technicality, but it's how it works. I mean, you cannot have this. I mean, you can. I assume that you could sort of cook up a model in which you can sort of do some sort of non-linear rate in which these things happen with the proper sort of delta T scaling. But yeah.
Yeah, you said that we have only one change per time. Is it?
Exactly. Yeah, that's
Yeah.
yeah.
Only one. We can only be birth or death.
Exactly, because all the everything else you would have, it would be order delta T squared, and that would sort of get.
Okay, now it's clear.
Okay, good. Thank you. Okay, so yeah. Okay, so well, this is perhaps what's the time? I think I'm going to skip this part, and I'm going to go into the analytical solutions because we have like 8 minutes left. So yeah. So there are several ways of tackling the analytical solution of the master equation when this can, and basically you can do this when the rates are linear. Okay, so when you have reactions of this type. Sorry, yeah. Well, when you have linear reactions. Okay, so in those cases you can use several methods, but one of them, which I like, this is a personal preference, but I like these methods very much, is using what it's called the probability generating function. Okay, so if you have some sort of this generating function quantity is used very often in sort of discrete mathematics. I found some time ago that they use it quite a lot in combinatorics and things like that. Okay, and it's defined in this way. Okay, so basically, if you have a discrete population, okay, with which can take n with n individuals, you can define this this object in this way. So it's P of n of t multiplied by Sn, and you sum overall n. Okay, so now in the case of the stochastic processes, the interesting thing about these functions is that you can derive a partial differential equation for this function. Okay, so and the way in which we do that is very easy. So consider the master equation that we just derived, okay, which is here again, equation 8. Now you multiply this by s to the nth, and so you multiply the equation by s to the n, and sum over all the values of n. Okay, and so if you do that and rearrange terms cleverly, right, like I did here, what you end up having is a PDE for the generating function. Okay, so for example, in this case, you can identify that this term here. So if you take lambda out of the summatory, okay, you can identify this term here when you sum over all the values of n as the derivative of g with respect to s. Okay, and the same thing here. Okay, the same thing here. You can, when you take sigma out of this summatory, what you get is that you have the derivative of g with respect to s. Okay, and here the same thing. Okay, so if you use this well, rather trivial result, what you can get is this this PDE for the characteristic function. Okay, is this clear?
Yes.
Yes. Well, okay. So this PDE in this particular case, so because well, you can the sort of you can very easily see that if you have nonlinear rates, things that depend on n squared or n cubed or whatever, here you're going to get extra terms with second derivatives of g with respect to s, or third derivatives of s with respect to s, and those in general you are not going to be able to solve them. But if the system is linear, sorry, if the rates are linear, then you only get here on the right hand side first order partial derivatives with respect to s, and this you can solve. You can solve this, well, using several methods, but it can be solved using the method of characteristics. Okay, and if the initial condition is this, so this initial condition, you can, if you go back to the definition of the characteristic function, you can very easily work out that this means that the initial population is exactly equal to, so you have a probability distribution in which you have exactly e individuals initially. Okay, so the probability of n being different of I is equal to 0, and the probability of n being equal to I at time 0 is equal to 1. Okay, so if you put that initial condition here for p of n of t equal to 0, you will work out that your initial condition is something like this. Okay, and in this case you can solve this equation analytically using the method of characteristics, and you get this very nice expression. Okay, and once you have this, you can recover the probability distribution using Cauchy's formula. Okay, so this function here has the probability that it's analytic in the interval 0, 1, I think. So you can use this form. Okay, and just, I think that this is, yeah, just to finish, I think one of the advantages of using this sort of formalism is that even when an analytical closed solution for this characteristic function is not available, you can use this function and its sort of PDE are associated with asymptotic methods of analysis, especially WKB asymptotics, which is a type of asymptotics which is useful when you have big systems. Okay, so for very noisy systems is not useful, but for systems that are sort of biggish, finite by big, they can be used. Okay, so I think that this is it for today. So I will in the next lecture I will give a little bit more of a formal definition for many of the things that I've been saying today, specifically what the Markov property means, how the Markov property is equivalent to this Chapman-Kolmogorov equation, and how you can derive from the Chapman-Kolmogorov equation the master equation. Okay, and then I will talk a little bit about this WKB asymptotics issue that I just mentioned right now, and that's basically it for today. If you have any questions,
so please let's thank Thomas, so you can open the microphone, and then there is a question on YouTube that I forgot. So let's thank the speaker, please, so we can know that. Okay, so Thomas, thank you, was great. There was a question in YouTube. I also have a problem to switching from one to the other. From Ricardo Rosa, that is asking, wouldn't birth and death be included in the complementary probability, like 1 minus lambda minus sigma, or something along with no event? We can interpret it as a net change?
I'm not sure I understand what he means by net change. But if
I can copy here in the chat.
This is if what you mean is this is a balance of probability. Okay, so this is a probability. So everything that you write in the right hand side of the equation has to be a probability. Okay, so the probability of so what I suppose that what you say the flux, you mean this. And this is the
yes, it's not my question, so
I thought someone was saying something.
Yes.
I suppose that when you said the flux, you meant this, and this is the proper again, because this is a probability. This is a probability balance, so this is kind of conditional probability. Okay, so this is the probability of the state at time t, and this is the probability of the transition. But the probability of the transition, for this to be sort of a proper balance of probabilities, the transition rate needs to be multiplied by the delta t, because otherwise you wouldn't have a proper balance of probabilities. Okay, so these W's are probability rates, so they are transition probabilities per unit time. So for those to be probabilities, you have to multiply it by something that, or integrate them over time, so that you get the sort of proper probability.
Sorry, I have a question which I think is similar to the one asked on YouTube, because what I get from what he's asking, and I think it's also what I need, like what I wanted to know, is so if we're saying, okay, so it's if we're in n-1 case, and then lambda is the probability to get to n, population n, and the delta t, then if you're in the n+1, then sigma, like sigma delta t is our probability to go up of 1. But I think the idea, like what he was asking, is whether that's like the last term we're adding there, so 1 minus and then the stuff times p, is then the term in some sense of probability that either nothing happens or even two reactions that balance out happen.
No. This thing of two reactions that balanced out doesn't happen. You can only
have
reaction. You can only so the idea here. So sorry. I mean this is. I have abused the notation. Okay, because I should have put here plus things of order delta t squared. Okay. So this idea that two things can happen at the same time. This is what we were discussing before. You can, in this formulation, you cannot have it. Okay. So in other, I mean, when I say in this formulation, I mean for a Markov process. Okay. In other more general situations, perhaps you can have this, but in Markov process, at each sort of you can only have one thing happening at a time. Okay. So again, we will see this in more detail, and which it will. So this is connected with the Markov process.
Yeah. Okay.
We will
Yeah.
see,
I understand.
We will see this when we do the Gillespie method. We will see this explicitly, okay? Because this is part of the derivation of the algorithm.
Yeah. I know that. Yeah. Okay. Yeah. Thank you.
Idea that two things cannot happen can happen at the same time. In a Markov process, they cannot. In other more general processes, they may. But here, no. So the probability of nothing happening is just this. And this probability of two things happening at the same time in this formulation are of order delta t squared or whatever. And when you take the delta t going to 0, they just. But the sort of the physical motivation of this, we will see it when we see the Gillespie algorithm. And then I hope that this.
Yeah, it's clear. Like that's what I thought, but I was just like I wanted to double check, and I think that was also what I got from the question on YouTube. So maybe that helped someone else.
Okay,
so
okay,
thank you.
One second. So Ricardo is still saying it is not agent-based model. It is just a number that counts.
No, this is not an agent-based model. In an agent-based model, you can have, in a cellular automaton, you can have whatever you want, because you sort of make it's rule-based. This is not exactly, I mean, I'm sorry, I have started, I thought this was going to be easier to just make an informal presentation first, and then going into the maths, but perhaps if I had gone into the maths first, now it would be clear. If you have the key here is the Markov property. If you have the Markov property, these things cannot happen. These two things at the same time or whatever. In a rule-based model, yes, there you can do whatever you want.
It was great talk. So I think that you hit the right level to.
You never know what's.
No, I know, but you know, there will always be someone that is more. No, that's we have a very broad audience here, so it's great, very inspiring.
Yeah.
So other question, but anyway, thank Ricardo also from YouTube.
Yeah,
Ricardo Rosa is our also faculty, is our colleague. So other question, the students, don't be shy. Vinicius, don't ask questions, strange. No? Well, I think that it was very clear. So can you send us the slides? So at least the students for next Thursday, they will.
Sorry,
can you send us the slides so the student can?
I will. Yes, I will send them to you.
Yes, and then
you can
spread it.
Yeah.
Okay, so let me stop those recordings. So thank you very much. So if no more questions for Thomas. People are a little bit more shy on the first lecture. You know, this is then the second lecture usually they get a little bit more courageous. Okay, so thank you very much for this wonderful lecture. Looking much for the second one on Thursday, same time. And so thank you everyone for the question and participation. So thank you Armando, also our colleague from outside UFRJ, from all over. And so see you on Thursday.
Yes, see you on Thursday. Thank you, everybody.
Thank you, Thomas. Thank you.
Bye-bye.
Thank you.
Cheers.
Bye-bye. Bye.